Hello, my name's Niall English and I'm the CEO of Aqua-B. I'm going to explain our biogas upgrade technology today, and it's all based on bubbles, tiny little bubbles in water at the nanoscale. And we call these bubbles nanobubbles because they're so small in the nano size range. And in fact, you wouldn't even be able to see them with the naked eye, unless perhaps you've got some laser diffraction pointer. Anyway, let me show you just one single concept slide, perhaps, to get the point across, as it were. So here we have essentially the concept, and what we have is some water coming in here on the left, and this water, for example, it could be wastewater, seawater, or relatively clean water. We mix that in with the incoming raw biogas, roughly 60-40 methane versus CO2, for example. And we actually form nanobubbles here in this unit right here, okay? And what happens is that we use our patented approach to form these tiny bubbles. I'll explain that in a minute, the basis of how this enrichment works. And then we have relatively pure CO2 that we managed to extract and draw out from the raw biogas in the wastewater, and then that CO2 laden water, if you like, can be used for various things. You could grow algae with it, for example, or you could form gas hydrates that I have here, effectively a type of ice with gas trapped inside it. And this actually purifies the water very, very well. And we end up having extraordinarily pure water that we can melt again and recycle most of the gas. And we have this in this type of system here. But what I mostly want to speak today is about the biogas upgrade process itself down here, where we form nanobubbles. So you might reasonably ask, well, this is some type of magic. How could you take most of the CO2 out of the raw biogas by forming nanobubbles, therefore leaving the residual gas as essentially pure biomethane, pretty close to grid quality with a low methane slippage? Okay, well, let me explain just for a couple of minutes the basis of that. So essentially we have imagine we have some water here, and the water can be at a certain level. We can even draw in a little meniscus here at the side to be realistic. Now, when we apply a DC electric field, DC meaning just in one direction, a static electric field with a vector, that actually causes a phenomenon known as electrostriction. And this causes the density of the water to increase. So therefore, what happens is that the water density increases and the water level goes down slightly in blue here. So effectively what we have is we have this sort of negative pressure region in green here that's temporarily at a negative pressure at the gas-water interface, okay? And this tends to draw in gas molecules, because if you have this type of slightly negative pressure situation here at this gas-water interface, with this negative pressure, you're effectively welcoming and sucking in gas molecules. It's a bit like having a straw. If you put a straw into, let's say, one of those Capri Sun drinks, you will, or the children put the straws into these small cartons of orange juice. You see them sucking in the orange juice or the orange drink, and effectively what happens is you're actually exerting a compressive stress or a negative pressure, and then you see the small carton or pouch of orange juice start to collapse under the negative pressure or compressive stress. And this is the phenomenon known as electrostriction, brought about by applying this external electric field, which is a bit almost like a child sucking through a straw, and the liquid level goes down with this green negative pressure region that sucks in gas. Now, let me tell you about the magic way in which the gas is actually sucked in, for that is the key of our patented invention. So, I can draw another diagram here, a bit related to that one, except now let's sort of consider more of a molecular scale, and we can draw the liquid level going down, let's say in blue, under electrostriction. Now let's picture individual molecules. For example, we have methane in red. And since biogas is roughly 60-40, I'll draw 3 methanes and 2 CO2s. CO can be in green here. Now, because CO2 has a quadrupole moment, and it also has oxygens here, then CO2 actually has a much more intimate interaction with water molecules. And these water molecules can have what's known as a hydrophilic interaction by setting up hydrogen bonds, for example, with the oxygens in CO2. In other words, the CO2 molecules are much more at home, if you like, in the water. And therefore, when it comes time to suck in with that sort of straw effect or electric field effect, the CO2 molecules are going to be effectively attracted to the water much more preferentially and much more selectively in the water phase, because after all, CO2 is more hydrophilic with these dipole quadrupole interactions, electrostatics of hydrogen bonding, whereas methane is much more hydrophobic. So hydrophobic, of course, is the Greek meaning fear of water. Phobia, fear of, hydro, Greek for water. So methane does not like being drawn into water. It's got a lower solubility. But CO2, on the other hand, is much more friendly with water for these chemical dipole, quadrupole interactions, electrostatic interactions, hydrogen bonds. So therefore, that is welcomed much more. So you have this effectively selective enrichment of the water mediated by the external electric field here. And that effectively draws in CO2 gas molecules in here much more selectively for that essentially electrostatic interaction, welcomes these CO2 molecules much more preferentially. So that's why we get this enrichment effect. It's a microscopic phenomenon at play here, effectively a type of molecular filter, if you like. So thank you very much for your attention. And with that, I shall leave you today. But of course, if you do have any questions on this biogas enrichment technology, do feel free to get in touch. And thank you very much. Do have a good day.